Thank you very much. So I'm going to talk about these plans we've developed for the United States to change the energy infrastructure for all purposes. That's electricity, transportation, heating and cooling, and industry. And also kind of lead into, we've actually now developed plans for 139 countries of the world, but they're not quite available, but they're almost there. I'll talk about them. So why do we care? Well, worldwide, air pollution kills 3 to 7 million people prematurely. Cardiovascular disease, respiratory illness, complications from asthma. In the United States, it's on the order of 60 to 65,000 per year. And this cost, based on statistical cost of life, about 3.2% of the GDP of the United States. Global warming costs are another, well, by 2050, the United States emissions alone will, by one estimate, cost about the world about $730 billion, which is right now the air pollution cost from the U.S. alone in the U.S. is about $500 billion. So they'll be about equivalent. Fossil fuels are finite resources, and their prices will go up over time just because they are finite resources. And we'll see that if we go to cleaner energy sources that have zero fuel costs, you stabilize energy prices. And also, there's a limit in the job growth due to fossil fuels, and we'll see. We'll look at job growth as well due to converting the energy infrastructure. So what's this idea? Well, the idea is to change all sectors to basically run on electricity, and then we'll use storage, low-cost storage, to fill in gaps when electricity is not available. So the electricity options for electric power, as we know today, are wind, concentrated solar power, CSP, photovoltaics on rooftops or utility scale, geothermal power, hydroelectric, tidal, or wave. For transportation, these, what we call wind, water, and solar electricity options will power battery electric vehicles and produce some hydrogen, for example, for long-distance trucking for some purposes, and by electrolysis, and some cryogenic hydrogen for aircraft would be one possibility. For heating, cooling, we'd use heat pumps, which run in reverse for air conditioning. Also, some of the storage options also provide cooling. Electric resistance heating and solar hot water preheating. These are all existing technologies, so I'm not talking about anything new. We're talking about repowering the whole U.S. with existing technologies and, in fact, the world. For industry, we'd use electric resistance heating and other types of electric heating for high-temperature processes, including arc furnaces, induction furnaces, dielectric heating, and hydrogen for some high-temperature processes. What about storage? Because people say, well, the wind doesn't always blow, the sun doesn't always shine. Well, there are actually low-cost storage options already available. I mean, batteries are the most expensive, so we would not use those very much, even though they're on this list. But, I mean, existing storage that is already cheap is hydroelectric power in dams, which we would not grow under these plans. There would be no new hydroelectric power. We'd just use existing hydro, pumped hydro, which also wouldn't change a whole lot. But molten salt for CSP, it's about on the order of $15 per kilowatt hour. I mean, compared to batteries are like $500 to $600 a kilowatt hour. PV, you can even use, because it'll be so advantageous, you can even use PV to heat up molten salt as well and then convert it to electricity at night, even though that would be less efficient than CSP. But it turns out that's actually a very low cost compared to something like batteries. And then hydrogen for transportation. But for heating, cooling, we'd heat, when we have extra electricity, we'd heat water, and that can then be used for district heating to, when you want electricity, you can convert that heat back to electricity. Or you can use it for hot water itself in district heat. Or you can make ice during the night when the prices are low and then melt it during the day for cooling. And chilled water does the same thing. These are, just to give you an idea, chilled water, it's on the order of $2 to $5 a kilowatt hour. So same ice is about $35 a kilowatt hour compared to batteries, which are $600. Or you can store heat and cold in soil for opposite seasons. Now, and then there's demand response management. Now, in terms of matching power supply and demand, this was a study we did a few years ago for California, looking at can we actually match the power demand hour by hour just with wind, water, and solar, and just the hydroelectric dams, and CSP was 3 hours of storage. And indeed you could, 99.8% of the hours of the year. The black line here, this shows 2 particular days. The black line is power demand on those 2 days. The light blue is wind, yellow is PV, orange is CSP, blue is hydro, and the red on the bottom is geothermal. And you can see you can match the power demand exactly. The natural gas for backup, which is the gray on the top, was never used except for 0.2% of the hours. And this, again, was without even using demand response management or any of these other energy storage technologies I was talking about, except for CSP and hydroelectric. Now, what we're not recommending, if you're fans of these technologies, don't boo me, is nuclear or coal with carbon capture, natural gas or biomass for electricity. For vehicles, any liquid biofuels of either corn or cellulosic or sugarcane ethanol or soy or algae biodiesel or compressed natural gas. And why? It's not because some of them might be better than what we have today in some respects, but others are actually worse. But it's because they're not so good as the wind, water, solar options. I mean, in terms of air pollution, for example, burning any type of biofuel in a vehicle creates more ozone because of the acetaldehyde and formaldehyde additions that enhance ozone formation. So you actually get more air pollution pretty much with any biofuel. And you'll also, the carbon benefit is not nearly so much, even if there is a carbon benefit, compared with electricity from wind, for example, using to power battery electric vehicles. And anyway, I can spend a lot of time going through each of these, but I'm not going to. Now, end-use power demand, if we actually do a conversion, you also reduce power demand quite a bit just due to the efficiency of electricity. So worldwide in 2010, 13 terawatts was the end-use power demand. And if you go to 2050, the end-use power demand for all purposes, it would be about 22 terawatts worldwide. But if you convert everything to wind, water, solar for electricity and hydrogen, you go down about 30% in your power demand. And only actually about 25% of this is actually due to the efficiency of electricity over combustion. So there's actually no change in your habits. About 5% is due to end-use energy efficiency improvements, which could be actually higher. In the US, you get about a 38% reduction in power demand. In California, about 44% reduction in power demand. Again, with only 5 or 6% of this points due to end-use energy efficiency improvements. Now, we did plans for every single state, looking at the current infrastructure for energy, then marching forward to 2050 for all the sectors, and then doing a conversion for each sector to different technologies. And then we have all the results. If you go to this website, 100.org, there's a map. And you can click on the state, and you can actually come up with the end-use, the power demand, or sorry, the end-use infrastructure for each state. But this summarizes the sum over all states, and in terms of what technologies would power the United States for all purposes. So we would power the U.S. for all purposes with 31% wind onshore, 19% offshore wind, so 50% of all power would be from wind. About 5% PV rooftop systems on residences, 4% on government and commercial buildings. And those represent actually pretty much the limits of how much rooftop you can cover in the United States. And this is not just electric power, remember, this is all sectors. And electricity today is only about 20% of total energy. So this represents about the maximum you can cover rooftops with. But then we'd have about 30% solar PV power plants, 7.5% CSP power plants, 1.3% geothermal, 2.5% hydro, and a small amount of wave and tidal power. Now the areas, these are the areas that would be required to power the entire US in 2050 for all purposes. The yellow is onshore wind, and most of that is spacing except for the red dot in the center, which is the footprint on the ground. But this is land that can be used for multiple purposes, including rangeland, farmland, and grazing land. And the blue is offshore wind. The orange in the bottom is CSP plus PV power plants. Those are footprint areas. And that represents less than 0.5% of the US for the PV plus CSP. And then the yellow is rooftop solar, which is on existing rooftops, and then there's a small amount of the rest. But this represents, in terms of footprint, less than on the order of 0.5% of the US, and in terms of spacing, about 2.5% of the US. But that spacing area can be used for multiple purposes. One of the benefits of putting lots of offshore wind farms is we did numerical simulations looking at the impacts of large-scale offshore wind on hurricanes. And this is a simulation of Hurricane Katrina on the left without any wind turbines offshore. And on the right, when we have a few tens of thousands of wind turbines offshore the Louisiana coast to the southeast. And you can see as the hurricane comes in, you start, and this is wind speed, you start reducing the wind speed where the turbines are, which is that triangular area up on the right curve. And then it turns out you start reducing the wind speeds, which reduces the wave heights, which therefore reduces convergence of the air to the center, which actually increases the central pressure, debilitating the entire hurricane, such that by the time you reach landfall, you've dissipated most of the hurricane with these large numbers of offshore wind turbines. Now, you need tens of thousands of these to have this big impact. So you're not going to have a big impact with just a few turbines. But they all pay for themselves because you put them up not to prevent the hurricanes or stop them, but to generate electric power year-round, so they pay for themselves from the electricity sales. And this is just an additional benefit, it turns out. Now, we've done, as I mentioned, plans for 139 countries, and I just want to show you one. This is the first public showing of this. This is a plan for China. How to repower China for all purposes in 2050 with just wind, water, and solar power. So you need about 127,000 5-megawatt onshore turbines and 150,000 offshore wind turbines. And 7% of the energy would come from PV systems on residential rooftops, 7% on commercial government rooftops. And then we'd have 34% PV power plants, utility scale, and 10% CSP power plants, and small amount of geothermal, about 7% hydroelectric, existing hydro, by the way, and then 0.3% tidal and 0.25% wave. So this is kind of just the first draft of this plan for China, but we're doing these and looking at a lot of other issues, including jobs and air pollution savings and things like that, which I'll talk about in a second. In terms of world resources available, the world has in high solar locations over land about 340 terawatts of power available. But in 2050, we'll need about 15 terawatts. So there's a lot more solar than we need, available than we need over land, and just alone solar. But we want to combine that with wind to address the intermittency issues. But there's about 70 to 80 terawatts of wind available over land in high wind locations compared to about 15 terawatts of end-use power demand in 2050 if we convert everything to electricity. So there's a lot of wind available as well worldwide. Now, what about the costs? So right now, these are the levelized costs, unsubsidized levelized costs of energy in the United States in 2013, based on Lazard. And you'll notice that wind is the least expensive form of electric power in the US right now, but it's half the price of combined cycle natural gas, which is 6.1 to 8.7 cents per kilowatt hour, whereas wind, the average on wind is around, actually closer to 3.7 cents per kilowatt hour unsubsidized, mostly Great Plains wind. Now you'll notice also that utility scale solar right now is about the same as natural gas as well. It's 7.2 to 8.6 cents a kilowatt hour. Residential solar and commercial are twice to 3 times higher than that. But you notice that the wind and the solar component at the large scale are very cost competitive now. Now, the other benefit of them is that when you add wind and solar, you have zero fuel costs, so you stabilize energy prices. So this can be seen in data. If you look at the 11 states in the United States with the highest fraction of their electric power from wind, the cost of electricity in those states has gone down about 0.4% in the last 5 or 6 years. All the other states went up 8% because you have zero fuel costs, and so you can stabilize price of energy. In terms of the trajectory of how we plan to accomplish this, by 2050, we want to have 100%, and by 2030, about 80% conversion. But this requires a rapid, immediate policies to be put in place to actually get this going. And to that end, well, I'm going to put up the summary in terms of jobs and the air pollution cost savings of about $500 billion and climate cost savings $730 billion. But you create about 7.5 million jobs, and you lose about 4 million jobs by doing this conversion in the U.S. So that's a benefit. But in terms of the policies, so as Professor Weaver stated, it's really a social and political issue, not a technological or economic issue. And to that end, I just want to mention, well, just yesterday in New York, Governor Cuomo banned fracking permanently in New York, and this was a step. And the reason he was able to do this is because there is an alternative now in names of these complete 100% energy plans based on wind, water, and solar. And so without that confidence of having such a plan, you would not be able to get the political will to actually ban fracking in the state of New York. So thanks.
Thanks, Mark. We have time for a question or two.
Mark, what's the amount of capital you need to mobilize initially? So you're presenting levelized cost estimates.
Right.
How much capital are you talking about?
In the U.S., it was about 15 trillion. Worldwide, it's about 100 trillion. I mean, that's if you upfront.
That's over 50 years?
Yeah, that's all the capital equipment you need for all the electric power generators to power the whole world. For all purposes, 100 trillion. In the U.S., it's about 15.
What extent does the slide involve retiring fossil
Yeah, well, part of it is all new electric power from now on, you'd put clean, and so that wouldn't require retiring. And then whenever something does retire over the next 40 years, you replace it with something clean. So, but then to really get an aggressive, this implemented aggressively, you do need to retire other plants faster than they would naturally be retired. So that is a cost that would have to come out of this.
What's the timeline from decision to implement this to zero emissions?
Well, the zero emissions occur in 2050, 80% reduction emissions by 2030 is, well, the goal. I mean,